All right. Before I start my presentation, I'd like to acknowledge all the agencies and the people that made this research possible. And, I tend to talk a lot, so I don't want to get cut off without saying thank you for all these people that really help a lot. There's no way I could have done this groupal effort by myself or just with my research group. Starting with the Bureau of Reclamation, which donated the land for us to do this riparian restoration technique. The Engineering Research Center for reinventing the nation's urban water infrastructure, headquartered in Stanford, California. The Sierra Soil and Water Conservation District here in TRC for helping us with drilling and tractors and leveling the terrain and things like that. The St. Cloud Zeolite Mining Company, since they donated about 2 tons of the mineral that we apply to restore, in the restoration technique. And the Mexican National Council for Science and Technology for funding me for about 4.5 years. Excuse me. So our focus of our research was to develop a technique where we use a geoengineering material to restore salt cedar clear areas. We all know that the riparian areas in the Southwest, especially New Mexico, have been altered. We know there's been channelization of the rivers. The historic hydrographs have been changed. And whether salt cedar is a cause or just a symptom of this degradation is still being debated. However, salt cedar is still being targeted to being clear. Therefore, that's the focus of our research. Where these sites are clear, usually we have problems after that. Oh my God, what am I doing? All right, there it is. Usually it's very difficult for pristine vegetation to reestablish back at these sites. Otherwise we'll have only weeds. Also, most of these areas remain clear, bare soil, and then we have other problems such as soil erosion or bare areas. So if we want to help restore these sites, there's a lot of challenges in this environment. For example, a limited amount of precipitation and the timing of precipitation. Sometimes the precipitation comes either too early or too late for these plants. In the spring, usually it's very dry. Before, there has been a lot of success with pole planting techniques. The folks at the Los Lunas Plant Material Center by the NRCS, they're getting 95% survival rates with pole planting techniques. The only thing is that you cannot grow grasses, and sometimes you want to grow grasses to have avoid erosion, or you want to put a cover so that other invasive species don't grow back as easily. So this method that we're proposing has certain advantages. For example, you don't need to use water. You only use water during the installation. And it's suitable for both shallow rooted plants or deep rooted. So what we did in this study is we took it from the lab to a pilot field study scale. The objective was to test whether plants grown in zeolite cores will be superior, have higher survival rates, will be healthier than plants grown in regular soil. We expect the plants in zeolite to be healthier. All right, so I'll start talking about the details about the technique. The study was located in the Middle Rio Grande Basin. We were in a site of 40 hectares. We were about 800 meters close to the Rio Grande, right here. This triangle is the area where we were located. It was right next to the little town called Las Palomas, between the Elephant Butte Reservoir and the Caballo Lake. And the interesting thing is there were mountains on both sides, some elevated hills dividing here the side from the I-25, and this recharge a little bit the groundwater during the winter. All right, so we started with a site that was very dry. It was a little bit more higher elevation than the floodplain, so the groundwater was shallow, but not too shallow for small shrubs to grow in. And the groundwater varied between 1.9 to 3.3 meters. The arid was semi-arid. The climate is semi-arid with about 8 inches of precipitation per year. Maximum temperatures reaching up almost 40 degrees, minimum there be between 8 to minus 20 degrees. And the soil at the site was, we had the top 60 centimeters were silty clay loam, and then underneath was a very coarse sandy soil. Okay, the experimental design that we did, we used 2 plots of 20 by 20 meters, and we designed a 8 by 8 matrix. So in every other column will contain the zeolite boreholes that I'll explain in a minute how we install it. And then the other ones was called riparian soil, or RS, as control. We chose carefully 4 plant species based on their capabilities. We chose Emory's Baccharis because it's an obligate riparian. So if this plant doesn't have moisture for most part of the year, they will die quickly. We choose a plant that is dominant in the area, but it still grows in riparian regions, Fourwing, Saltbush, and 2 grasses, giant saccaton and saltgrass. Saltgrass was, we just took it from a meadow that was adjacent to the site. The other species we took them, we acquired them from the plant material centers. So they were very good stock. We ended up with 8 treatments, 4 species with 2 substrates. So we have 4 and 4, and 4 specimens or 4 replications. Okay, and this study lasted for 2 years, 2012 and 2013. We started in January 2012, and with help with the folks from the Sierra Soil and Water Conservation Service, district, sorry, we drilled up to a depth of 6 feet with this auger. However, we still didn't reach the groundwater, so we had to manually, painfully, drill with hand auger bucket augers to go all the way to 8 feet and find the groundwater. Then we pour the dry mineral. We gotta be, very carefully to shake it well so that there were no gaps, no air gaps to hinder the capillary rise. This is the mineral right here. And after 40 days, we noticed that there was moisture already almost at the top of the surface for most of the boreholes that we check. There was a previous study done by another graduate student at NMSU who he recorded a capillary rise of 5 feet in 40 days and up to almost 7 feet after 1 year in small 2-inch PVC columns. And this is a picture of the plants. These are the shrubs, two different types, and the giant saccaton. They were still dormant when we plant them. We plant them around March 15 for both years. On 2013, we replaces the plants that die on the previous year to complete back those set of 8 plants per treatment. We apply 1 single irrigation of 1 gallon per borehole, not because the zeolite needed moisture, but because we wanted to uniformize the moisture for both treatments, zeolite and just control course. Here is a picture, some pictures showing how we planted the grass and a Fourwing Saltbush. I'm not going in chronological order, but the next more important thing for us to test whether the plants in zeolite were doing better than in riparian soil was to measure some parameters. Of course, survival was one of them. And then the next ones was growth, because growth was something easy to measure since the beginning of the transplanting. We tried to use leaf area index, but there were no leaves at the time. So we instead we used the leaf chlorophyll content, LLC, using a chlorophyll meter. And on the shrubs, we use a pressure chamber after the methodology by Turner, 1988. But we only could do this for the grasses because for the shrubs. The grasses had very small leaves and require a completely different methodology. Also, before we even do that, we have to install a weather station and moisture sensors and piezometers to measure the depth of groundwater. Here are some of the sensors that we use. This is a 15 feet tower with solar radiation sensors, wind speed, wind direction, solar panels. Here, these are the two data loggers that collected the data on 1 minute, in 30 minutes and 24-hour periods, and the rain gauge. For the soil moisture, what we did is we took randomly, out of all those 8 specimens, we took one. So we had one profile that where we could monitor the moisture within the root zone to a depth to 3 feet. And we ended up with a total of 4 profiles in zeolite, 4 in riparian soil for both plots. This is the sensor that we use, and this is how we install the sensors to different depths. We install at 15 centimeter depth, 30 centimeter depth, and 3 feet, or 91 centimeters, sorry. I'm mixing units. This is one of the piezometers in one of the plots. We started with just the well, taking manual readings every 2 weeks, and then on July of the first year, we introduced these automatic pressure transducers so we could take measurements every 30 minutes. Okay. The statistical analysis was a little awkward because you have groups of observations that change over time. In 1 week you have certain survival rate. The next week you have a less number than what you started with. So we tended to use more non-parametric tests rather than the other type. We first separated the survival rates between the 2 years, 2012 and 2013. The 2012 was done as a sampling without replacement because they were just the plants that we put in. But 2013 was a combination of the 2012 and the 2013 plants. So it was with replacement. So we will see that the survivals were a little bit higher here because of you have a combination. But we did not divide the vegetation parameters based on the date. We just took for that day a sample and we just consider them all equal. Because the survival is, we consider it as being a binomial, either death or survival. We use binomial distribution test. And we use Mann-Whitney-Wilkinson rank test for the vegetation parameters, which many times had a small number of observations. Okay, these summarize our results for the plant survival rates in treatments. The results were not as expected. One thing that I need to mention is that since the moment we start the observations until the end of the year, the first year, the groundwater had dropped about 1.5 feet. So that really disconnected, went below the depth of the columns, the zeolite columns, and disconnected, reducing the extension of the capillary rise. We thought that all the plants were going to probably die, but surprisingly, the Emory Baccharis was able to put roots long enough to tap into that water. And we had very good successful rates, 6 out of 8 versus 2 out of 8 in the plot 1, and 7 versus 2 on the second cohort. And in the plot 2, which plot 2 had even a deeper groundwater table, we saw very, very low results, maybe between 0 to 60% survival. For the other grasses, the grasses were affected because as soon as the groundwater will drop, the moisture will drop, the roots that were only a half foot, a foot and a half will desiccate. In terms of the Fourwing Saltbush, these plants were very resilient. They just didn't die. So the Fourwing Saltbush, it kind of backfired on us because we had no deaths in both treatments. All right, this graph shows a little bit of what was happening inside the profiles at different depths. This line shows where the depth to the zeolite boreholes was at 2.4 meters. So whenever we went below, we had a disconnection. We can see, for example, on this point, the moisture at the shallowest soil was really low, and some of the grasses died. From this period, we had a very good connection. And in addition to that, you can see that the deeper the soil is, the more moisture you see. This confirmed that the theory that we saw in the lab really worked in the field as well. Okay, just to wrap up, these are some pictures of the results we have in terms of the plants. This is the plant that is obligate phreatophyte, and they grow very well in the plot 1, which is the shallowest groundwater table. You can see that they bloom, they had seeds every year. This is a plant that in the other control course, and they were significantly different for both years at plot 1. For Fourwing Saltbush, we found that the literature review says that these plants have morphological leaf adaptations to cope with extreme drought. So they have an increased water use efficiency. So when the groundwater dropped, they were not affected. Therefore, they both were equal. You can see after the rains in 2013, they really grew and took over. There were spaced 5 feet between each of them, and you couldn't even walk within the rows. For the grasses were really low survivals, 0 to 37, 38%. Of course, they were not greater than riparian soil. But we did notice one thing. We noticed that as long as the groundwater remained connected, these plants wouldn't die. The plants will be well. Once the groundwater dropped, then the plants die. So this gave us hope to say, okay, if we have a good connection, we're going to we can grow grasses even with the short roots. Pretty much the parameters have the same correlations as the survival. Baccharis is the only one who had some higher growth and higher less stress. Let's call it hydric stress, mid-day stem water potential. The conclusions of the study were that the survival and the growth was greater in the Baccharis. The Fourwing Saltbush, because of physiological adaptations, we didn't see any changes. And the grasses seem to respond better when we have greater connection. So this gives us hope for application of this. The good thing about this method is it doesn't require watering. It can be used for grasses, which is a novelty, and it can be combined with other methods as well, like the pole plant technique. You can use this for the grasses and the other method for the shrubs. That way you can maximize your cost. Some publications that talk about how we measure the hydraulic properties of zeolite and how we can use it as a great amendment in agricultural soils. And this will be published hopefully soon. And are there any questions? I'll be happy to respond.
All right. We have time
Do you think this zeolite would work with the willow cottonwood pole plantings?
Yes, it will for sure. Just like the Baccharis, and those are even more resilient than Baccharis. But if you can explore, if you can grow them tall, like the folks at the NRCS, Plant Material Center, then you really don't need the zeolite. If you have, let's say, if your groundwater is 7 feet deep, you can push them into the capillary fringe, and most likely you have a high success rate.
Have you or anybody from your lab looked at changes in soil salinity as a result of the wicking and evaporation?
We haven't, but what we have analyzed the mineral, sent it to the lab and stuff, and we found that the sodium content of this mineral from Winston, New Mexico, is kind of low. So we don't see any potential threat. However, it's really important that you analyze properly the zeolites because they all vary. And there are some in other Western states that have a high sodium content. So to begin with, you're not going to get good results because the salinity is gonna hamper the plants.
I was more referring to, so the groundwater coming up and then evaporating out, you're wicking water from the column all the way up. You've basically got a capillary fringe to the surface. So with evaporation and ET losses, salts that may be in the water that you're wicking up that might get left behind.
So it's coming from the source of the water, not from the zeolite. We haven't looked at that yet because this was just a pilot study, but I think it will be a great idea for a long-term study, which we wanna continue, see what happens after 4, season 5, different 10 years.